Welcome back, everyone. This is the second video for Chapter 5 on heat and matter problems. Let's do a pressure problem. The formula for pressure is force per unit area. So force divided by area, where area is equal to length times width. Here's our problem. Calculate the pressure when there is 5 newtons of force being applied to an area of 5 meters by 2 meters. So here's our formula. Pressure is force divided by area. Let's calculate our area first. Length times width, which is 2 meters times 5 meters, which is 10 meters squared. We're going to plug the area into our formula. Pressure then is 10 newtons, that's our force, divided by, oh, I made a mistake here. This should be 5 newtons. All right. So this is 5 newtons, not 10 newtons there, divided by 10 meters squared. And when you take 5 and divide it by 10, you get 0.5 pascals of pressure. So please note there that we have 5 newtons of force and not 10. Sorry about that. Let's go on to a density problem. Density is mass divided by volume. Here's a formula. And volume is length times width times height. Or you could, in some situation, you would use water displacement. So here's our problem. What is the volume of a material with a density of 1.9 times 10 to the 4th kilogram per meter squared and a mass of 15 kilograms? So in this case, they're giving us density, they're giving us mass, and wanting to solve for volume. All right, so let's rearrange that equation to solve. So rearranging, you get volume as mass divided by density. So we put 15 kilograms in for the mass, density of 1.9 times 10 to the 4th kilogram per meter squared, and we get a volume of 0.00079 meters cubed. Let's do one more density problem. Here, our problem states, what is the density of a material with a mass of 3 kilograms and the dimensions of 0.2 times 0.02 times 2 meters? We plug in mass at 3 kilograms, and then we have to calculate our volume. Volume is length times width times depth or height. And so 0.2 meters times 0.02 meters times 2 meters goes down here in the denominator. And when you take 3 kilograms and divide it by your volume, you're going to get a density of 375 kilograms per cubic meter. So heat is energy, and it is unique in that it cannot be efficiently converted into mechanical work. And so they have a whole science called thermodynamics to calculate heat engine efficiency. We're going to do 2 problems here to determine the maximum heat engine efficiency. Our formula, let me grab a pen here. Our formula is the maximum efficiency of a heat engine is 1 minus the ratio between the cold temperature and the hot temperature. These are reservoirs, the cold and hot reservoir, where TC is the exhaust temperature of the gas, TH means T hot is the intake temperature. So here's our problem. What is the efficiency of a heat engine with an intake temperature of 500 K and an exhaust temperature of 100 K? First of all, you have to figure out which is your T hot and which is your T cold. All right. And in this case, when we say intake temperature, that's your T hot. We always exhaust in a heat engine at a lower temperature. So this is our T cold, 100K. We're just going to plug the numbers into our formula here. So you have 1 minus the ratio of 100K, that's our absolute temperature, divided by 500K, and that gives us an efficiency of 0.8. If you multiply that by 100, 80% efficient. Let's finish off with a little more challenging heat engine efficiency problem. In this case, we have an intake temperature of a gas for a heat engine with an efficiency of 0.5 and an exhaust temperature of 1,000 degrees. They are asking what the intake temperature is. That's what they want us to calculate. So this is a little more challenging. And so we're going to first of all have to rearrange our formula to solve ultimately for T hot. So I'm going to recommend subtracting 1 from both sides. Here's our starting formula. So I'm going to subtract 1 from here and from here. So you get maximum efficiency minus 1 is equal to negative T cold over T hot. So let's plug in our efficiency of 0.5 minus 1, and that becomes equal to negative T cold over T hot. 0.5 minus 1 is negative 0.5. If we plug in the T cold, the exhaust temperature, it tells us, is 1,000 K. So that's T cold. Exhaust is T cold. So 1,000 K divided by T hot. Now we're solving for T hot, so I'm going to multiply both sides by T hot. All right, and so you get negative 0.5 times T hot equals negative 1,000 K. Divide both sides by negative 0.5. That gets rid of the negatives over here, and T hot ends up being 2,000 K. And your intake temperature had better be higher than your exhaust temperature, or you've done something wrong. So this is acceptable. We have a higher intake temperature than an exhaust temperature, so that is the solution for this problem. That's all the problems I have for Chapter 5.